Okay, right now we are going to look at a real-world example. This is example 4, and from the Glencoe book, what we're really looking at here, this is chapter 1, section 4. So as we continue to look at chapter 1, section 4, and what we're looking at here are minimums and maximums, extrema, and so forth. So I'm just going to draw just a couple of things over here. If you have polynomial that looks like this, we are looking for points such as that and that, so maximums and minimums. And if we read this story problem, what we're trying to do here, we're looking at the volume. So if you have a square piece of paper, a rectangular piece of paper, 12 inches by 8 inches, and you're going to cut out corners, and each one of those corners is a square that is x by x. And then you fold up the sides. So you would fold right along this dotted line here, this dotted line, dotted line, dotted line. So you'd fold those up. So you would have a base of 12 minus 2x, and this side would be 8 minus 2x. And that's because you're cutting off an x on each side. And as you did that, the height would be x as well. So you're trying to find the volume of that box, and you want to find the maximum. So the volume is going to be length times width times height, which is, so we'll do down here, volume with respect to x is going to be the height of x times 12 minus 2x times, I'll put it down here, 8 minus 2x. So that will be a third degree polynomial. We could multiply that all out and we'd get something x to the third plus something x squared plus something x plus something. And we could do that, and then we could look at that and see what it looks like. But a third degree polynomial with a leading coefficient positive, it's going to look something like this. And we'll graph that, and we want to find the maximum volume, which is going to be right here. So let's pull up the calculator and just type into the equation. So we've got x times 12 minus 2x times 8 minus 2x. Now you could multiply all of that out, and that would be great, but if you do that, it's still the same equation. We're just going to put it in here and graph it. Now I have the standard window set, negative 10, 10, negative 10, 10, and it's going to go ahead and graph here, and it looks kind of crazy. So as we look at that, let's figure out what the relevant domain might be. So we'll go over here and we will put in the domain for this function. The domain, so the smallest x can be is 0, because you can't cut out a square smaller than 0. And then if you look at the short side here, which is 8 inches long, the biggest x you could cut out of that would be a 4-inch by 4-inch section, and that would actually be kind of crazy, because then you would be cutting out the whole thing. You'd just be folding it in half. So the relevant domain has to be between 0 and 4. So let's go ahead and change our window for x. Let's go 0 to 4. And then for y, volume can't be less than 0, so we'll go 0. And I don't know how big it's going to go, so let's try 100. And let's graph that. Okay, this is looking much better. So the relevant domain for the function that we have, v of x is equal to x times 12 minus 2x times 8 minus 2x. The relevant domain for x is between 0 and 4. And then the volume, we're going from 0 up to 100 for v of x. And what we're trying to find here, again, let me move this over. It says here, the problem says, determine the length and width of the box that will allow the maximum volume. So we want to find the maximum, which is going to be up at the top. So let's take our calculator, and to find a maximum, we can do second calculate. Maximum is number 4. Then we have to find a left bound and a right bound, so we need to be left of that maximum. So we'll scroll over here to the left. We'll hit enter. You don't need to be real precise on this, as we have talked in class. So let's continue to go over. And that's looking for the right bound. So we'll do the right bound. So you have those two lines. You need to be in between them. So we'll just go to a guess. And the guess does not have to be close. It just has to be between the two bounds. Okay, so now what we get here is a maximum where the x value, and we'll go over here. So this is at a maximum when x is equal to 1.5694. We'll go out to 10,000. It's 1.5694. Okay, so if that is the x volume, the question that we have is what are the dimensions of the bottom of the box? So this longer side is going to be 12 minus 2 times 1.5694, and the shorter side is going to be 8 minus 2 times 1.5694. So let's figure out what those are in the calculator. So we'll pull that back up here, and we will clear the graph, and we'll go 12 minus 2 times 1.5694, and you get 8.861, which is, that's the only one that works there. So just to check, let's do the other side. 8 minus 2 times 1.5694, and that equals 4.86. I forgot to write this one in. 8.86. So your answer is B. And just to review what we did, we needed to find the x value that gave us the maximum volume. So we had to come up with a volume equation, graph it, and find the maximum. So that is how you attack this sort of a